often not totally obvious to me what background people have, so feel free to ask me to elaborate on anything that might come up. And if something is particularly interesting and you'd like me to talk about that more, feel free to say so as well. A lot of this is best with laptops, so if you have your laptops, that would be better. This is basically the agenda. So first we're going to go through a discussion of architectures, and these are basic vision architectures that every model uses in some way. Once you understand really just like the basic vanilla architecture, the entire world of multimodality becomes unlocked because multimodal models just like use the same pieces of various combinations. So it's really useful to understand what a vision transformer is. Pretty great detail in language, it's not really different. Finally, difference and similarities with language Mechanistic. This one might be more clear to people with a language background. So if there aren't as many language people here, I'll keep that part shorter. Part 2 will be interactive, and we'll actually be running some code on our own images to see if we can determine how the model is processing. Right here, we have a sneak peek of what's coming, and this is a sparse autoencoder feature that localizes like animal tongues. I used to think they were all dogs, but there's like a tiger like lurking in the corner. It's really just animals. And these are some of the features you can find and actually manipulating to influence your model's prediction. Okay, so here, these are some useful links. We'll be referencing this stuff throughout as we go throughout. Let's get started. So let's do a brief overview of vision architectures. You're familiar with the transformer. Are you familiar with transformer architectures? And it's okay if you're not. I'm just trying to get a sense of how these help. So 1-ish. Okay. Here's your transformer. It's the same architecture as a language transformer, except there are a couple of nuances. First, there's tokenization. So how do we tokenize images, right? For language, we have our pre-trained tokenizer. Here, we're just dividing the image into non-overlapping patches and then flattening the patches. And we're going from convolutional layer to linear embedding. So there's no dictionary matrix or anything that you see in language. There's no visual dictionary. Vision is a continuous space, which makes things a little different. But this here is how we're creating embeddings. We create these embeddings, and then we basically add this patch and the position embedding. This is called the CLS token. And here it's the 0 token. It's usually pre-appended to the whole sequence. And this token will accumulate global information throughout the entire image. And this is eventually what we're going to feed into the ML classification head to do if it's image net 1,000 byte classification. CLS token is pretty analogous to like the beginning of sentence token or the end of sentence token, but it's very functional in the prediction. And it's a usual transformer architecture. So we have a series of these like transformer blocks, and the information goes through each transformer block and is added back to the residual stream. And the slight difference here is that your attention, unlike language, it's not a unidirectional attention because it's not a sequence, it's bidirectional attention. So information is flowing both ways because you don't have this like causal sequence. And that makes things a little annoying from a Mechanistic perspective because you don't know which way information is flowing, but it's okay. It's something that we will learn to deal with. Just for context, this is like a vanilla vision transformer. This is like your basic, a bunch of people are just like, okay, language, this works in language, the sequence works on images, and it does. This is just the most vanilla architecture ever, but there are 2 variants that are worth discussing. One is CLIP, which the name of which you probably hear all the time, and it's basically this with a few more nuances, and the other is Dino, which is totally unsupervised. So CLIP and Dino are not going to actually be the focus of the workshop, and all of the notebooks and tutorials and stuff are on the vanilla vision transformer because it's so simple. But if you deeply understand this, everything else becomes very easy to understand because there's slight variations on everything. Yes.
So the linear prediction is just a singular embedding?
This?
Yeah.
Yeah. It's just like a single layer, like convolutional embedding. So you're going from patch by pixel, this is often like 32 by 32 pixels, to linear embedding.
And the extra learnable class embedding, what is that?
Yes. So that's just an embedding that gets optimized through training, and it starts off with a blank slate initialization, and basically through attention, it starts accumulating the information of all the patches to make the global prediction as to what class the information is. Yeah, no, these are great questions. Keep them coming. Okay, so here's CLIP. And CLIP is interesting. It's co-optimized with language. I'm going to take like a bunch of these image caption pairs, like a picture of a dog wearing a fabulous jacket, and I'm going to do this time have 2 encoders. One's a text encoder, which is just a classic text transformer, and the other is a vision encoder, which is just a classic vision transformer like we saw earlier. And I'm going to train them both at the same time. So I feed in the text, I get a bunch of text embeddings. I feed in the images, I get a bunch of image embeddings. And I put them on this matrix-like thing. And the correct text image caption are on the diagonal, right here. And the incorrect are off the diagonal. So this is an incorrect caption, and it's the correct caption. This is a picture of a dog wearing a fabulous jacket. And I'm basically going to train it by using contrastive loss, and I'm going to train it to push together the correct text caption there, so to push apart the incorrect ones. Effectively what you're doing is you're creating the shared text image space, where both your text embeddings and your image embeddings are now mapped to the same space and somewhat correspond to each other. And this is like incredibly useful for a bunch of downstream applications. The embeddings that emerge from this can be used downstream in the diffusion model, generate images. The interesting thing here is vision transformers, they don't generate images. They generate embeddings that can be used to generate images from a diffusion model. And that's one thing that was a little bit confusing, because unlike language, which generates text, you're not actually generating anything. You're generating an embedding.
But then how do you using this embedding, how do you then generate some data?
Yeah, so that's where the diffusion model training comes in. The diffusion model itself is out of scope for this, but the diffusion model, you're basically taking the embedding and you're training a model to associate the embedding with like a certain type of image using like a forward and reverse diffusion process. So you're like slowly adding noise to an image and getting the model to predict the noise that is added. And then to generate the image, you do noising, which is you start subtracting noise. And I would say that's a scope for a different workshop. There is a version of a vision transformer that generates images like language in the sense where you can sequentially generate each patch. It's called IGBT. It was the first image generation model by OpenAI, except it's very unstable. But it might work at very large scales. But at the current scales, at least what's been released, it doesn't really work that well to just do the language thing. Yeah, I don't know. Finally, this is a different architecture. This is the last architecture we'll go over, and I just want to mention it because this is considered state of the art. This is called Dino. It's by Meta. And what is important about this architecture is that it doesn't use labels. The past two architectures we saw, this needs captions, so like clip is trained by scraping the entire internet, and this need classes, so you need like ImageNet classes. But for Dino, you don't need any of that. And Dino's like trained in a really weird way, and I won't go like too deeply into it because it's not really the focus, but it's just worth bringing to your attention, where you have two ViTs, same architecture, you have a teacher and a student, and then you give them the same image, except you give the teacher the entire image, and you give the student a bunch of crops, or like augmentations of the image. So I might give the teacher the full image of a cat, and I give the student zoomed in random cat photos. And I find this so interesting because you're not co-optimizing it with language. And I think co-optimizing models with language is such a deep and philosophical thing because you end up adopting the semantic space of language. And as we know, like language can be like biased in some unique ways. But here, all your biases are like from perception or like from the raw data itself. You don't get the biases of the English language in your model. Potentially Dino is less biased in bad ways. Potentially it's less biased in good ways as well. But I consider this model more of an alien and less of a human. All the models that are co-optimized with English are very English human. So studying the differences in world models between Dino and a vision transformer is something that I very much am interested in doing. And if anyone has any interest in that, I'm happy to talk. Okay, so there are still a bunch of random architectures. There's a whole zoo, but it's actually not that complicated. Like we really just need to focus on like a vanilla vision transformer, and everything else will follow. So we have IGBT, which is this like auto-regressive thing. It's most similar to language because you end up predicting the next patch. You have stable diffusion, which is used downstream of the clip vision embeddings. You have Flabon, which uses like a vision encoder, and PolyGemma also uses a vision encoder. One of these multimodal models will first encode vision embeddings and then project that into this multimodal text image space. Not everything uses a vision encoder, like Flamingo doesn't. And Chameleon is like the weird one that is like the shared text image encoder, unlike the other models. Okay, so we're focusing on vision transformers and TinyCLIP. I would say like they're basically a vanilla vision transformer and CLIP are basically the same thing. Just CLIP has been like co-optimized with language, and we're gonna very quickly go through TinyCLIP and watch how information changes as it's processed through the layers. This is a very tiny clip. It's only 8 million parameters, 10 layers, 256 residual stream, which is like very small. For context, the GP is too small, it's 100 million parameters, so this is like 10 times smaller. This was trained on a distillation loss of a larger clip, so it's still pretty accurate. but it's very useful for Mechanistic because it's so small, so you can do a bunch of shit to it without burning that much compute. I've just been training like star software coders on this tiny thing because it's very cheap too and very efficient too. And you can see, as you'd expect, it starts off relatively uninterpretable and then it becomes more interpretable. This graph is a little weird because it appears to like start pretty interpretable and go down and then get more interpretable. But what's happening here is that people are saying, oh, it's picking up on edges or on textures, therefore it's interpretable. Here, it's picking up on some mess of things, and God knows what, we don't actually have the English language for it. And then here it starts picking up on more and more human concepts.
So this is as determined by humans?
This is as determined by humans.
Okay.
Yes. So there are some nuances there. This is like a subjective evaluation.
Yeah.
But yeah, layer 0 are like textures, and this is just, I don't know, like edges and like textures and like various things. It's often not super interpretable and like very low level features. And around layer 3, you start seeing these spatial understandings of the model. And by the way, these are collected by maximally activating patches. So we feed in 50,000 images, and we go neuron by neuron, and we collect which patch is activating the most. And then we return that patch, we return the corresponding image. So this neuron here is getting almost these segmentation map understandings of structure of the image. Or it's, oh, here's like a background, here are like stairs. And this neuron is super weird because this neuron is picking up on the position embeddings. It's getting like the rightmost column no matter what the content is, which I just find like super weird, but I think the position embeddings are like doing some work there. But it's always the rightmost column, so that's like a different like type of feature. These like position features and these like structural features. And as you go higher, like this here is picking up on cracks in the floor, but it's like all of these like models have, all of these images have cracks on the floor. And here, this is a very polysemantic neuron. It's picking up on green mountains and text. And so we're starting to see some polysemanticity. And this neuron here is picking up on signs of the tennis court, America is dead, like all these like shop signs. So it's starting to get more interpretable. And this is the final layer. It's only 10 layers, this model. And this neuron is picking up on a bunch of stars. What I find so interesting about the neuron is that, keep in mind, every image is based on patches. And here, the car information gets moved onto the monkey. The monkey's actually sitting on a car. At first, I was like, what the heck? Why is it returning a monkey when everything else is a car? And so you realize the monkey's on a car, and you're like, oh, the car information has gotten moved from the car to the monkey because those are the maximally activating patches. So the spatially local information doesn't necessarily stay there because all the patches are talking to each other during cross-attention, basically. Yeah.
Can you try to use gradient descent to create an image that is maximally activating for this neuron?
Oh, like the deep dream stuff? To create images?
Yeah.
Yeah, I think that's a useful technique. It's when you forward propagate
To the input.
into the input. Yeah. I feel a bit mixed about that technique because I feel like there are a bunch of papers suggesting it's unstable. And I do think that technique is interesting and underexplored in the sense where I do think it follows the loss landscape in the sense there might be like multiple local minima or saddle points, or it might be like more complex than just one class. But in practice, I've found the maximally activating image technique to be like more robust than feature visualization, although feature visualization has also been shown to somewhat corroborate these results.
So when you talk about like the patch size of 16, is this 16 by 16 or like 4 by 4? What do you mean by patch size?
Ah, yes, this is 16 by
16 by
16.
16.
Yeah,
Okay,
that's a
nice.
great, that's a great question. Yes, so like, the images for our all intents and purposes, not in production, but for our toy models are 224 by 224, and 16 by 16. You're doing 16 by 16 pixels for the 224 by 224.
Cool.
And this results in 196 patches, or you could do 32, which results in 9 patches. Yeah.
Cool.
Yeah.
Here you're not visualizing the CMS token?
Yeah, that's a great point. We're not visualizing the CLS token. It's a little incomplete. Yeah. I'm not sure how we would visualize the CLS token. We can visualize the classification maybe, but given that it doesn't correspond to any specific part of the image, it's not clear how we would visualize it. On our attention head visualization, we just have the entire image light up anytime you hover over the CLS token. But yeah, okay. These are great questions, guys. Please keep them coming. Okay, now we're going to just do a brief overview of vision Mechanistic techniques. And if you are familiar with Mechanistic, a lot of this will seem extremely familiar. If anyone has done the ARENA curriculum, a lot of this is inspired or derived from the ARENA curriculum. And if you haven't done language Mechanistic, welcome to Mechanistic. It's super fun. I'm glad that you're here. Okay, so we're just going to do this in 3 parts. I have 3 Jupyter notebooks. The first is like a main demo, which has like Logit attribution and causal ablations, and we'll go through something called the cat-dog switch, where we'll make the model flip its prediction from a cat to a dog by making like the minimum possible change to the internals of the model. And then we're going to do an emoji Logit lens, which is seeing that different patches correspond to different predictions. And finally, we'll look at some attention heads. So for notebooks 2 and 3, here's where I recommend having your laptops. And here's where I recommend actually running your own images, because it's just fun to feed in like a photo of your face and see like what it classifies things as. It's oftentimes really surprising or just like amusing. Okay, let's start with notebook 1. And here's where we're just going to do these kind of techniques that are very classical Mechanistic. So you're welcome to follow along here for this notebook or follow along on your laptops. It is fun to run live and then make small tweaks and stuff. But this notebook just walks through everything we just talked about, including vision and anyone who's familiar with language, how it's different from language in all these subtle ways. We're loading in what's called our hooked ViT. So for people not familiar with Mechanistic, we basically take the model and then we have this library. This is Prisma, it's based off transformer lens that hooks all the internals of the model, so you're efficiently caching activations in every layer. And we want to cache all these intermediate activations because they contain information about what the model is doing at that given moment. So we're loading in this time your vanilla vision transformer, no clip nonsense, just like a vanilla vision transformer. It's trained on ImageNet, it knows 1,000 classes, it gets 75% or so, or 72% accuracy on all these classes. It's 12 layers, 12 attention heads. This is the exact same architecture as GPT-2 small, except for your bidirectional attention. Okay, so we're gonna feed in this image. This is gonna be our cat-dog image, and we're gonna try to flip its prediction. We feed it in, we tokenize it. Our patch size is 32, so this results in 49 patches. It's 32 by 32 pixels, non-overlapping. And then we're just gonna test it, okay? What is the classification? And it's classifying things as tabby cat with 34%. And it's 11% Bernese Mountain Dog, and 7% Border Collie, 6% Egyptian cat, Collie, Tiger cat. Does anyone know what an Attribution is?
Sounds German.
I think it's a kind of German dog, but I don't know. But anyway, all these predictions seem like pretty reasonable to me, but I am curious why it picked tabby cat instead of dog, because I would think it would classify it as dog, because there were just like more dog patches, so why is it classifying it as cat? I don't know. I'm really curious how this neural net makes this classification. I'm going to run the model with cache, and this means that I'm collecting all the intermediate activations in all 12 layers, and I'm going to collect my ImageNet indices using this functionality, and then effectively what I'm going to do is I'm going to calculate like the raw Logit predictions. For anyone familiar with like how transformers work, you get your Logit predictions at the end, which you feed into a softmax. And our Logit predictions and Mechanistic are such an important metric because they're telling you what the model is predicting. And we tend to use Logit predictions and not softmax, it just tends to be more stable. Here are all the Logit predictions for all 1,000 classes throughout the model. So you can see the model starts out relatively uncertain. That's fine. But then as the information goes through the end, it starts becoming more confident in its predictions because the Logit values start getting really either positive or negative. And around layer 11, it gets super confident in certain things. Like Bernese Mountain Dog right here, it's very confident in this prediction. And like what's down here, it's less confident, I don't know, whatever, Kubas, Malamutes, like a bunch of dogs and cats start appearing up here as being very confident, and then it makes its prediction. By the way, when I say Logit value, it's like how does layer 3 have a Logit value? We're effectively taking the class token and we're feeding it into the MLP to get a Logit. And Mechanistic literature calls it like direct Logit attribution. So yeah, let's plot a tabby cat, a border collie, and a banana just as a sanity check. And you can see like the Logits remain relatively low until you get to around layer 8 and you start seeing some separation. It doesn't seem to really matter. It seems around layer 8 something's happening in the model. Banana goes down, the model goes, it's like not a banana, but border collie, tabby cat like starts skyrocketing.
Really super stupid question. So here you have your patches going and you're trying to predict the next patch. What is happening again in the vision transform? Are you thinking of words already? So this is classes? Maybe I missed the first one.
Yeah, no, that's a great question. Yeah. So you're not trying to predict a patch in the next patch, which is kind of the language model. Yeah. You're just trying to predict the class.
So you do have the classes information for each patch? Or?
We only have the class information for the CLS token. Okay. These are great questions. So the vision transformer has hard-coded 1,000 classes, and it's been trained on ImageNet. 1,000 way. And the way it's trained is that only the CLS token goes through the MLP for classification, and the loss function never directly sees any of the other patches. It only sees the CLS patch.
So I guess like, yeah, empirically it seems like you do find that some of the other patches have reasonable information to correspond to classes, but a priori that's not obvious how it happens. So can you, like, why do you expect that to be the case? So, I'm like a bit confused actually.
Oh yeah, sorry, could you repeat it one more time?
Sure. The original information took like 100 and something patches plus the CLS patch, and the CLS patch, you know, that should, if you unembed at any point, it should, well, I think what we know is that you unembed at the rate any, then this corresponds to the class, and you might hypothesize if you unembed early, logic lens style things, that you also get something that represents the class. I guess it's not super obvious to me why you took a different patch, which is not the CLS patch, and do this unembed, it's anything meaningful, like it needs to be like the same space, if any in that sense, like an unembed should operate meaningfully on it.
Yeah,
And
okay,
thinking
no,
about what
that's
is true.
an incredible question. I actually was really skeptical that it would work. I was like, why would unembedding a random patch lead to any meaningful prediction, given that it was going to be optimized for the CLS patch?
Yeah.
Is that what you mean?
Yeah, exactly.
So I was also really skeptical. I wasn't expecting anything, but empirically, when you actually do it, like when you actually feed the patch tokens in, you get meaningful structure. This is feeding in every patch into the classification head, and it's, oh, this is cat and this is dog. So the CLS token itself might be classifying this whole thing as a cat, but all the dog tokens on the dog are getting classified as dog. So an emergent segmentation map is getting optimized out of the prediction. And this was surprising. I'm like, why? But it appears like this is a side effect, even though it's not directly optimized for. And the patches are all communicating with each other through attention at every point. Yeah.
So the thought is that if you dump some information about cats on the cat patches, then later the CLS patch and then grab that information by your attention or something like this. It's like,
Yeah.
what's the story? I thought it was the story. It seems
The
plausible.
story is like why this information is staying there localized.
Yeah, this is pretty amazing. I think.
Yeah, it is pretty amazing.
I think it makes intuitive sense, right? Because the class token is going to be the same shape and structure as the visual blocks, and they're going to have the same operations that done on the mass equivalent to the transformer. The only differences are going to be in the positional embeddings, and I guess like there's probably a class token embedding. But like otherwise, like they're doing like very similar tasks, going through very similar operations. So that's not a formal argument, but it makes the whole sense to me. That makes sense.
The sense where the same operation is being performed on like the CLS token and all the other tokens. So
Yeah.
the spaces should be
The
similar.
transformer architecture is like kind of agnostic about the tokens. It's the only difference is in means that's agnostic.
Don't know. I understand what you're saying. I think it's like a somewhat satisfying explanation. I don't know if it's as satisfying an explanation as what you're all looking for. I don't know what a satisfying explanation would look like.
Yeah, again, wavy. It's like it's what's going on in my head.
Yeah.
I guess if this is true, then why don't you take your vision transformer and like why don't you just put observation pressure on every single patch? Like why not do that? Like,
There are
obviously,
some
because-
versions that do it. There's
Okay.
global average pooling, basically, where
Yes.
you average all the patches and feed that in.
Exactly.
And that works pretty well. But weirdly, the CLS token works better, just empirically, at least at the scale people were looking at. I don't know why. Maybe because averaging sends it like somewhere weird in the semantic space. But people do global average pooling.
Okay,
Yeah.
that's cool.
But this wasn't optimized for global average pooling, which is like the weird part. This was optimized just for the CLS token. And yeah, I don't know, but takeaway from this is that emergent capabilities are like very real. And Sora, like physics comes out of Sora, despite Sora not being explicitly optimized for physics. So if you're optimizing for some objective, a bunch of other like random shit will happen. Maybe this is an AI safety problem, I don't know. But yeah, if you could think of even more satisfying explanations and that can be empirically tested, I'd be like very curious to hear them. Okay, these are Logit scores. We went through that. Okay, the Logit differences. Let's see, where shall we? Okay, this graph has like a lot going on, but effectively what we're seeing is the ranking of every patch. The red and the blue are the rankings for Tabby Cat and Collie, and this graph is a little hard to read, so I apologize, but the silver are the Tabby Cat rankings for every other token, and the gold is the Collie rankings for every other token. This was before I did the dodging lens. The dodging lens, in my mind, was like, oh shit, I can actually now see what's happening. Before I was like caught in this world where I had no idea what was going on. But what I do find interesting is some patches are very much not border collies and cats, and we'll see later that they're often random predictions, submarine or something. Okay, this was like, we're still trying to figure out ranking, like how are the patches ranking. Then I'm like, okay, on the patch level, so on the y-axis we have the patch number, there are 50 patches, and on the x-axis we have layer number. And I was like, okay, how are the patches transforming for their predictions if I were to like feed them into the NLP at any given point? And you can see, like before, like layer like 10-ish, they're all random. Like we have a llama, we have an overcoat, we have over this, we have fox, we have like bulletproof vest. We just have like nonsense. And basically the Logit lens is like nonsense for like layer like 11-ish or 10-ish or so. And I suspect it's because the basis vectors are rotating to the extent where they're not aligned with your output space. But this is something that needs to be empirically confirmed. So if anyone wants to work on this, this is something that I think is like, super interesting.
How would you confirm that?
Linear probes or tube lens. So if the information is there, a linear probe should be decently accurate on our layer layers instead of this nonsense. And maybe taking like the KLD versions of linear probe predictions with like Logit lens predictions would be good. Or tube lens, where you like fine tune on the intermediate activations. Because they just might be a different distribution or like rotating basis vectors due to the linear projection after MLP out and stuff. So yeah, getting this working out would be really great. The other hypothesis is that it actually legitimately is nonsense into layer 10, which would be interesting. And that seems like strange to me, but maybe that's happening. So here is our Logit lens. Finally, this is like my favorite visualization because as you can see, I went through 5 visualizations before I'm like, okay, I can see what's going on. And this patch here is like aircraft carrier, and this could actually make sense because it could be the statistics of that background do map to aircraft carriers. It really could be. And yeah, I find it interesting that dog information is stored in the background as well. Here is like the same visualization, except now it has like a heat map. No, wait, it doesn't. This one has a heat map, sorry. These are some Emoji colors. So yeah, it has a heat map, so yellow is most confident, and the most confident tokens are here. And it's like very unconfident in these dog predictions, even if they're dog predictions. Okay, how are we doing on time? All right, let's finish up this notebook and move to the interactive stuff. Very quickly, let's go through the cat-dog switch. I'm like, all right, I'm gonna subtract the difference between a cat minus dog to get a sense of when the model decides I'm gonna classify it as like a cat or a dog, because it's pretty confident in both. So it's like, all right, how is it actually deciding to classify it as a tabby cat? And it appears like it classifies it as like a tabby cat throughout most of the model. Down here, a negative Logit score here means that it's a tabby cat, and a positive Logit score means it's a dog, because I just subtracted them. But there's a brief moment in layer 11 where it briefly classifies it as a dog, and then it switches like back to cat. Something's going on in layer 11. Maybe we can like zoom in and figure out what it is. A lot of Mechanistic Interp is like localizing where in the model key computations are happening. So we can localize where in the model where it's happening. So now we're doing a head attribution where we're basically projecting the output of every attention head. We're projecting that onto the final layer to get a Logit score. And here we're projecting the Logit difference. So the Logit difference is, okay, layer 5, something intense is going on. We can start zooming in. I'm gonna go through this relatively quickly because we'll go through this in like more detail on our own images later. But we can start visualizing. We're like, okay, here's an attention head in layer 11. This is layer 11 and 4. And it's okay, this is super bright. And as you can see on the pink square, the cat's face is very highlighted. So it's like, all right, the cat's face might be like pretty key in it deciding it's a cat. This might be, the model's like, okay, this token's like very important, and this is going to make me like upweight the fact that this is like a cat prediction. And here, I find this kind of really weird because if you look at the pink, it's localized on this background.
So this is the final layer?
This is layer 11. Yeah.
Out of 12.
Yeah.
Wait, there's like 11 zero index?
Yes, zero
So it's the
index.
final layer.
Yeah, it's the final layer.
Yes,
Yeah.
okay.
It's the
So
final attention
then,
head.
so actually in this case, like, there's no further like information passing that happens after this layer. So like the only thing that matters is the information needed to the CLS token.
Exactly, yeah.
Yeah, okay, so I'm not trying to read that chart then. It seems like the only information that actually matters is where you move things from to the CLS token, and the CLS token doesn't appear on this chart, I think.
Yeah, that matters. Information flowing from the CLS token to the other tokens wouldn't matter in this layer.
I am also saying information flowing from one token to another token also doesn't matter.
Yeah. Yeah.
Yeah. Okay.
Yeah.
I see.
Yeah, that's a really great comment. The information, so if the information is flowing from the cat head to all the other tokens, this is actually super irrelevant.
Yeah.
But it is flowing to all the other tokens, including the CLS token, which is relevant. But yeah.
Yeah. Okay.
Yeah. Great. That's a great point. These are great questions. Okay. It appears that information is flowing from the cat base to the rest of the patches, including the CLS token, although the other patches are irrelevant.
There seems to be another column that seems to be relevant. Is this changes the top?
Yeah.
Oh no, this is still the cat.
Yeah,
Head,
it's like,
top of the head.
yeah, it's like the top of the head.
Yeah.
Yeah, these attention things are so weird because they like wrap around, where it's like often not obvious what things are unless you highlight over them, which is partially why interactive makes it so much more fun. But yeah, it appears like these two tokens are like getting moved to the CLS token, which might contribute to the cat classification. And then this attention head is also important. I found this attention head weird because if you look at the pink, it's this random background token, but it's super active. And there is a phenomenon in vision transformers called reservoir tokens, or tokens with a very high norm that encode a lot of information that are actually just like in the background. But the vision transformer is using them as like memory or as a scratch pad or basically as an ad hoc CLS token because there's nothing there. It can use it as free memory, and these are called reservoir tokens. I think language does this too. It stores information in like periods and punctuation and stuff. But in vision, it's like really pertinent and it fuck up your attention map sometimes.
But is the second column that's activated for this head? The dog.
I think it's a dog face, yeah. Okay, so. All right, so I'm gonna really give a really high overview because I want to like get hands-on with stuff and move on to that. But just the last section is like activation patching techniques. Anyone familiar with Mechanistic is familiar with this, but if you're not, it's basically injecting into the model corrected activations to try to like causally get the model to change its prediction. We end up cropping out the cat, and cropping out the cat fucks up a bunch of things. We localize it again to the final attention head layer. This time it's head 4, and if you keep like localizing this, you can keep localizing things to the patch level. And you can get more and more localized to the point where you're like, okay, patch 26 is fucking everything up. And what is that? Oh, patch 26 is the cat face. This is a really key token of the model's prediction. And if you actually zero it out on the query token and like, replot things, basically you end up flipping the prediction. It is like the TLDR, that one cat face token, if you zero it out, go from predicting it as a cat to a border collie. But it appears the final layer is pretty essential and a bunch of subtle things are happening. Of information of important patches is going to move to the CLS token. That's this demo. I recommend checking it out and actually playing around with it or doing your own images with it if you want to dive further. But for the rest of this specific talk, the last 2 parts of the talk, if you have your laptops, I recommend getting them out and actually writing some of this code. The first thing I recommend is doing the emoji logic lens and actually writing it with your own images. And these are like the patch level predictions we're talking about. It's the code feeding each patch into the classification head and giving it a class. The link to the demo is here. So maybe we can do that for 15 minutes. And then for the final 15 minutes, we can look at some attention heads because there's some like really gnarly shit going on here in terms of like corner attention heads, modulus attention heads, all this geometric structure that's emerging from the images. And just like looking at these, running your cursor over them is a good way to get an intuition of how information is flowing. Let's actually run this maybe, and let's just open it. I recommend finding your own images, and the way you load an image is you find the URL and you just do wget, so you just replace this in image of your choice. So we can run any image we want. Does anyone have any image that they want to see run with the emoji logic lens? I'll just like Google it and get the link. Does anyone have any? Maybe I want to see like a polar. Yeah.
The famous monk picture from Vietnam. Maybe that's a bit personal.
The famous what?
Monk. There was a monk to protest the Vietnam War who just poured gas on himself and just sat there on fire.
Okay. Is anyone?
Oh.
Would anyone rather not use this? Okay. Maybe we do something less gruesome. But you can do it. You can do it for yours and let us know what it's predicted. For the wider audience, I'll do something less gruesome. But you should. I encourage you to do that.
Circus scene?
Circus?
Yeah.
Circus scene? A circus scene or a specific circus? like
Yeah,
this.
this is-
All right, I'm curious what this is, especially because this is out of distribution because it's not naturalistic. Maybe it'll work, maybe it won't. I've had mixed results. It's trained on naturalistic data, but sometimes it gets artificial data.
So maybe these look very generic.
Yeah, okay, maybe something like this will work. Or, I don't know, something like this. I don't
How about
know.
Shoggoth?
AI circus?
Shoggoth, the monster with the mask.
Shoggoth?
Yeah.
Okay. I don't know what. Okay, I don't know. I don't know how we got here, but okay, we can try this. I don't know what the model is gonna make of this. Like, why not? We're here for experimentation. So let's first confirm that this link is working, and let's now get this. Everyone, find your own image. You can be as gruesome as you want if you're doing it privately. Just yeah. And I'm gonna zero all of this out. Actually, I'm sorry. I'm realizing this is the master copy, which I should not do. So I'm gonna save a copy in my drive. And if you are running this, I'd also recommend creating a copy as well, just so you can save your results. And I hope my master copy did not fuck everything up, but we should be good. Okay. Now I have my new copy. Let's run it all. Manage sessions. Let's terminate other sessions. Let's go. Let's go. Run it all. Let's zero all of it. Let's get rid of this. Let's add this. We'll call this Shoggoth JPEG. Maybe it's just loading libraries. Let that load. Yeah, so this is just a bunch of plotter code. Libraries, here we're just loading some image transformation code just to make sure it's in the right format. We're loading our hooked VAT. You can load whatever model you want. You can load CLIP as well. The CLIP Logit lens requires actually different code because you're projecting it into a continuous semantic space, not 1,000 classes. So you can still do it, but there's just a little bit of a nuance. You're taking cosine similarities with your resulting classes, which can be completely arbitrary instead of 1,000 way. That's the great thing about CLIP, is that the Logit lens is way more nuanced. Let's see. Loading. If anyone manages to get their Logit lens working, feel free to say so, and potentially we can share it on the big screen as well. Drop a photo in the chat.
You have a big dictionary, which is image net class to emoji or something, or how does
Yeah.
a JSON behind it? Okay, I see.
Let me actually, while we're waiting, I can bring it up because it's funny. I basically just asked ChatGPT to generate it back in the day, but there is this here. It's under utils, data utils, ImageNet to emoji. There's just this giant ImageNet dictionary that will give you the class, but if you hover over it, it'll give you a more specific class. Yeah, it's somewhat coarse-grained in the sense where dog maps every emoji, but if you hover over it, you should get the official thing. Where are we here? What is it now?
I got a decent result on Spider-Man meme.
Oh, nice. You want to drop in a photo?
Yeah, it's in the Slack.
It's in the Slack. Okay. Oh. Okay. Interesting.
Wait, is that the one the visual means?
So it's classifying all these as comic book. That's what book means.
Oh, nice. Okay.
That's really good. How is the second to last layer? Because often the second to last layer is more accurate. Because I think the last layer, the segmentation map gets eroded in the last layer, while the second to last preserves it due to whatever optimization pressure is happening. But yeah, door here, that's pretty accurate. I'd be curious what all these, oh, it is a card. It's a card in the background. And boxing glove, I don't know, maybe he's fighting, weightlifting. I'd be curious as to what these mean. I'd be curious as to what this random dog is doing there, even though that's not a very confident prediction. But it seems most confident in the fact that this is NYPD. I'd be curious what this is right here.
Recreational vehicle.
Recreational vehicle. And these are fire trucks?
Yeah.
Okay. Not bad. That's really not bad.
I
Okay.
feel like the weightlifting thing could be the stance that it's taking.
Right. Yeah, it's like a fighter stance. And like here's also like a fighter stance.
Yeah.
Yeah.
It's interesting that they're different.
Right, yeah, it is interesting.
And then the same one gets repeated for the other guy.
Right here.
And then there's like a heel boot the other, the fourth one.
What is this?
That's dumbbell.
Dumbbell?
And the boot is cowboy boot.
Red cowboy boot.
Okay, that's fair enough. I think that's fine. Okay. Interesting. Wondering why the
We're
Shoggoth.
missing the O side.
Oh, I'm missing the O. Do what?
In your W get.
W?
In your
Yes.
W get command.
Oh. Oh, great details. Okay, here we go. Yay, okay. So now I'm gonna collect all the intermediate activations and I get this tensor, which is like one batch, 50 patches, 13 layers, 1,000 possible classes, and I'm gonna display, oh god, okay. Sturgeon, it thinks it's a fish, it thinks it's a sturgeon. Just for context as to what a sturgeon is, a sturgeon is...
Did you learn this for this work, or did
This.
you know this before?
A sturgeon? I'm just learning what a sturgeon is right now. I did not know what a sturgeon was until 2 seconds ago, but this
They're
is
most famous for caviar coming out of them.
yum. It's very yummy. Okay. Maybe the Shoggoth was based on a sturgeon. I think that's like totally fair, and it thinks this is an isopod, hippopotamus, rotisserie, butcher shop, hog. Okay, some of these predictions, I mean, it could be a hog. Okay, I think it's
I guess it's picking up on like flesh, lumpy flesh.
yeah, sea lion, lumpy flesh, all these like lumpy animals like hyenas. Combine a hyena, hippopotamus, a sturgeon, and an isopod, and you would get the Shoggoth. Given that it's not been trained on a Shoggoth, I think that's like an okay decomposition of what a Shoggoth is. That's, yeah, its main classifications. Oh, sloth bear is very high. Sloth is high, hippopotamus is high, and like sturgeons, there are like a lot of sturgeons here. What is nice? Imogen will teach you so much about the world. Okay. So yeah, okay. So this like kind of works. So if anyone else has like interesting predictions they'd like to share, we can do them. Otherwise, we'll move on to the attention head visualization and yeah.
I posted my cartoon Shoggoth in Slack.
Oh, okay.
It was a mix of
Oh.
predictions and being very confused.
Okay. Very nice. Does any of this make sense to you?
A scorpion makes sense. Snake. There's one of them that's nematodes. That's nematode worm / roundworm that makes sense. There's a few texts that kind of make sense. So there's like various like preview creatures that are there that track. But there's also gun, which it doesn't make sense, and strawberry, which doesn't track at all.
Interesting. Because yeah, this is also super out of distribution because it's just a cartoon, right? It's not like a naturalistic image. Yeah, I'm surprised it really got made any sense of this at all. Okay, so we have this one's quite good. Houses. Nice. Is this the last layer or is this the second to last layer?
It is the last one.
It's the last layer. Yeah, I'd be curious if the second to last layer is a little better. So you just do like -2 in the layer prediction. But yeah, so in order to change the layer, it's just some like fun syntax stuff. We end up changing the layer down here, like layer index, here it's -1. For the fruit bowl example, if we change it to -2, it debatably gets more accurate in that it classifies these as like red wine and not strawberries, and there are more figs. The -2 predictions are sometimes a little bit better, depending on things. Okay, we have another one. We have a polar bear. Nice. Okay, this is pretty solid. I guess the foxes are Arctic foxes.
Yes, I think that's right.
I'm curious. This looks like a very last layer prediction. I noticed on the last layer, like all the patches start flipping. Well, it's second to last. It's a little bit more for segmentation map.
And sorry, how are you saying that we changed that?
Ah, yes. Display grid on imaging heat map. There's this one layer label here called layer index.
Yeah.
So if you make it -2, it gets the second to last layer. And you can make it -3 as well, which is like the third to last layer. And you can watch the patch predictions like start flipping basically. Yeah. But yeah, okay, guys, these are fun. Let's quickly move to the attention head visualization because we have about 15 more minutes, and we can do this for 10 minutes and then take questions. Here's the interactive attention head tour, and this specific model actually uses ImageNet, which is built in. You're welcome to use ImageNet, or you're welcome to use your own image, depending on what you want to see. And here, I believe this is some mantis. This attention head is one that gets the midpoints of the image. This attention head, for example, so this attention head demo, you can basically just load in your attention head index. You load in the batch index, but you can also, let's go back up. So you have your model. Here we're loading like a tiny ImageNet just for like RAM constraints, but you can load in whatever image you want using the wget functionality from the previous notebook. We were just like processing the batch to be 224 by 224 and putting it in a data loader, and then we're just like putting it into the image. You can replace this ImageNet functionality with just whatever image you want, and then you can visualize all the attention heads at once. This was the visualization we saw during the lightning talk. It is 12 layers on the y-axis and 12 attention heads on the x-axis. And you can see that the attention is like quite geometric and picking up on these pretty geometric patterns until it gets more and more complex. And we can see that it's really fun to explore attention heads. We can specify the attention head index. This is between 0 and 144. And visualize what it's doing. And this one's picking up on the corners of the image. If we look at the pink, which is the key or source, we can see that it's picking up on the corners, and right now it's picking up on the 2 midpoints, and it's picking up on the upper 2 corners as well, and the CLS token is decently active. Yeah.
I don't understand the thing about picking up on the corners.
Yeah. It appears that the values for the corners all have a uniform attention value, if that makes sense. So if you look at the actual pink, which corresponds to the key, this column here, when I make the key constant, but I keep changing the query, it appears that the corner is like querying the entire image, if that makes sense.
Yeah.
And that applies to the other 2 ones. And the attention pattern is like relatively uniform.
So you said basically what you're saying is these are acting as, so just vision people call these like registers, language people call these like attention sinks?
Yeah, I'm not sure if it's a register, because my understanding is registers are just like high norm tokens. Here the norm isn't high, it's just like consistent. Like it appears to be almost like triangulating, almost like coordinate style. Like here are the corners, here are the midpoints. It's like keeping track of that information in this specific computation. This is in contrast to an attention head that's like this, for example. And this appears to be keeping track of the fact that the image is wrapping around itself, in the sense where if you look at the pink, every time the pink jumps to a different row, it corresponds to a different square in the attention head. So it seems like each attention head is keeping track of different, almost geometric properties of the image. I don't know if that makes sense.
What do you mean by keeping track of?
Or at least mirroring it in its attention pattern, basically, potentially for some downstream mutation. Or the structure of the image. Maybe instead of keeping track of, that language is like a little ambiguous or anthropomorphic, but the structure of the attention pattern is mirroring geometric properties of the image that weren't explicitly hard-coded.
Okay.
Yeah.
Or it could be that all of that is useless.
Yeah, but I guess that was my reading of it. That like it's just the corners aren't very useful for actually making predictions. So you just like chuck empty information there, or maybe just do a max polling or something there.
Yeah.
Average pool because attention is like divided by. Yeah, I don't know. I can't quite understand the hypothesis right now. I'll read through the thing and then like.
I think it's perfectly plausible that the corners are useless and it's like downweighting them. It's weird because like this blue attention score is like mid-level, but I do think it's interesting that it's like consistent. It could be like
attention, right? Like on the score, like they normalize the scores, aren't they? So
yeah, but yellow means it's like a higher score.
So is this before you do the
This is before the
normalization?
softmax.
Oh, okay. Before the softmax.
Yeah.
Do you have a picture like after the softmax? So I guess that's what actually moves things.
Yeah, so this is the same attention head post softmax.
Okay. Oh, great.
So this is the CLS token, and basically everything has been zeroed out.
Yeah, so I guess I would say that the things we were looking at before were actually like insignificant compared to the CLS token.
Yeah, it could be. To be honest, I'm actually a bit confused about it because it's like, if this didn't matter, why is it there? If that makes sense? Like, why is the structure why does a geometric structure even appear if it just gets deleted afterwards? Which makes me wonder if the post softmax information needs this corner information in some ways, maybe to delete it, but it needs to know that it's there and it exists in order to create this post softmax output. But I don't actually understand yet the relationship between keeping track of corners to actually producing this like post softmax thing.
Yeah, I think that might be a bit of a red herring, to be honest, because maybe we should talk about this after.
Yeah, no, it's a really good point, because is this a red herring and it's just is it functional? My suspicion is that it's functional, because why else would it, even if it was that big phenomenal, like why does it appear?
I think what I think is happening is that if you have more things that acted on the row, then that means you're allowed, that's like offsetting. So if you only want to apply 0.5 for the class token, there's no way of doing that apart from like having other things like, because you get average. So if you need to offset that by having things elsewhere to get, if you really want, if the value you want is like 0.5 of the value, then the only way to do that is to like have some random stuff that makes it do the 0.5 because it sums to 1. I think that's how I would do things.
And you think that's going to be consistent across images basically, and it's really what it's optimizing for is like summing to 1.
So it's optimizing the amount that it wants in the first column, and then like it has to, everything else has to sum to 1. So,
I see.
You'd like have to just throw some nonsense everywhere else such that things add to 1.
Interesting. And it could be that like significant information just isn't in corners and midpoints or something. Like why does it pick like corners and midpoints as? I get what you mean now by like register token. Like it's like it's a register token in the sense where it's storing some computation, but it's not relevant to the image itself.
Exactly. Yeah. When people lose attention sinks, so you might get
Attention
up to more
sinks.
of what, like, yeah.
But why is it picking such a geometric coordinate system to do the attention sinks?
Because the ones that it doesn't, they're like where the most useless information is, or like where it doesn't matter if like overwrites the corners because there's nothing there to.
With the corners, do you mean the 4 corners of it or all the edges?
The 4 corners specifically. If you look at the pink, there are these like 6 little blue columns. 1, 2, 3. Here are the points. 4, 5, 6.
Yeah.
And Chloe's hypothesis is that this is like an attention sink where it's not actually optimizing for any content of the image, but it's trying to optimize for the computation. It must be summed to 1, and it so happens that these corners and midpoints aren't really containing information, so they end up getting optimized to something that would sum to 1. So it happens to it's detecting corners, when really it's just the side effect of it needing to sum to 1. It's an interesting hypothesis. Is there a way to test something like that?
Yeah,
try to find images that have significant texture in the corners so that it can actually be used as a register block.
Yeah, so the other way that the way that, this is basically seen as a goal in some sense. So what people have done since then is to actually just give it extra space in computation, and then they find that we do less of this using the other space for the computation you need to do. But to test that, you need to train a whole new model. I mean, we don't really do that. But it's like something about this, like, I think we should show.
I'd love to read it. There's one in Vision called Vision Transformers Need Registers, but it's not about attention sinks. So
It is, I think.
Oh, it is the same paper?
It's the same idea, but they have a different name for it.
Okay. Cool. No, I would love to read papers like that because I feel like there's so much of synergy between language and vision. So it would be cool to like write a vision version of this where it's, vision papers have attention sinks as well, and they manifest as these geometric patterns that look like they're detecting the coordinates of the image, but really it's just some byproduct of optimization or something. That would be like a cool workshop paper or something.
Can you pick different and interesting images for each attention head?
Sorry?
For each attention head, have you picked some interesting images, or is it just randomly chosen?
These are just randomly generated. Like this notebook is like less selected than the emoji ones, where these are just like random, whatever the data loader for ImageNet gives me. So this is the same attention head, but it's just like a bunch of like random ImageNet images, and it appears like similar. There are similar patterns in every image, which is why this one, interestingly, is less prominent. I do not know why, but it is somewhat there. And like, the dark seems to be corresponding to suppressing whatever the object is.
It just suggests that nothing's paying attention to that, right?
But why is it so geometrically uniform, if that makes sense?
Corners
Like the
are
corners,
not missing.
yeah.
Like just nothing is paying attention to it.
But consistently corners for every image, and it's I think it's unique, if that makes sense, where it's not every attention pattern shows corners. This one does not pay attention to corners either, if that makes sense. It's a consistent suppression, if that makes sense. And I think that consistent suppressions are significant in their own way. While this one isn't a consistent suppression, it's just seems to be like noting that the image is wrapping around itself, or it could be something else. The corners of the image have more background information, and it's picking up on that. There could be multiple hypotheses at play, for sure. But the sort of thing to draw attention to is that in this attention head, the corners are not significantly not noticed, if that makes sense, which makes me think either they're functional in the computation or they're like epiphenomenal in optimizing for something. But I'm inclined to think they're not epiphenomenal because they're so consistently geometric. But anyway, we can discuss that after. It's about 1 minute, so the end of our workshop is here, but I encourage you to play around with this because there is a lot of weird stuff. And I think you guys are asking exactly the questions we need to be asking because I don't see enough people investigating this. And I myself don't have the best answers yet, but would really like best answers. I love to see people run ablations on some of these things, which might give us hints as to whether any of this is being used functionally, changing the norm as well, if it's optimizing for the norm. It would be very interesting. And yeah, are there any like final questions for the overarching with vision? The last thing I want to draw attention to is like there is this last run post that has this library laid out and it has like a bunch of open problems at the end. There are places to get started, and I would love to see more people working on vision. So if anyone is interested in looking at these research questions and talking more, I am around. The final thing is that we have SAEs next week, so just training smart asylum coders on vision and getting very fine-grained features because the stuff we saw was not fine-grained at all, really. And we are recruiting collaborators for this Prisma library. It is a vision version of Transformer Lens, and it makes running ablations or doing direct Logit attribution very trivial. Oh yeah, feel free to reach out. Feel free to talk to me at any point. And are there any follow-up questions? People online as well.
What are the different Prisma transformer lenses?
It's mainly just like all the transformers are hooked. Yep. Well, for Transformer Lens, they're not. For Transformer Lens, there's a bunch of tokenization functionality that is relevant for language, but it's not relevant for images. There's a bunch of visualization that's vision specific, like Logit Lens, like various attention head visualizations. You could definitely work Transformer Lens and report over all the models. That might be like 3 weeks of work, maybe, or 2 weeks of work, maybe depending on how hacky you are. So you could definitely repurpose Transformer Lens for your own purposes, but there are a bunch of subtle things, attention being different. Like architecture is different enough where it would require some dev work to get it to the point where you can use it. Yeah. Okay. Thanks everyone. Thanks for the questions as well, and thank you for the clarifications. It's still like a very active and developing area of research. I don't have answers for a lot of them, but I would like love to see more work. So yeah, feel free to drop papers in the Slack, and thank you everyone for coming. I appreciate it.